Okay, so the last lesson in this unit is basically the exact same word problems you did in grade 11, but instead of degrees, they're in radians. So you have your, for example, those Ferris wheel problems, the tide problems, basically a lot of circular motion problems. They're coming back. So I had some guidelines here, but they're really the same approach you would take for solving any word problem. The one thing I would really emphasize is a graph for the trig function would be really helpful. So the water depth in a harbor is 21 meters at high tide and 11 meters at low tide. One cycle is completed approximately every 12 hours. Find the equation for the depth as a function of time hours after low tide. So, you know what? Let's just give ourselves a graph. So, height or depth. Let's do D instead of H. So the depth of the tide. It starts off, so hours after low tide. Okay, so time is hours after low tide, and we said low tide is 11, high tide is 21. Okay, and we said the period was 12 hours, so max. And in fact, you don't need these values on the t-axis, but I'm going to give it to you anyways. This is going to be 6 because it's halfway between 12. This is 3 because halfway between 0 and 6, and this is 9 because it's halfway between 6 and 12. And this here is halfway between 11 and 21. So average between 10 and average between 11 and 21. So that's 32 divided by 2, so it's 16. So that makes sense. 11 plus 5 is 16. 16 plus 5 is 21. So the numbers show that this is a symmetrical wave. And see, it's going up by 3, 3, 3, 3, because 3 is the quarter period. So everything's checking out. Everything matches up with what I learned earlier about graphing trig functions and deriving the graph from the equation. Okay, so let's do it. D of t equals, they don't specify for sine or cosine, so I'm going to do cosine because I don't have to introduce a horizontal shift if it's cosine. So it's 5 cos. The period is 12. So let's do the calculation for k here. 2 pi over 12, which is pi over 6. So k is pi over 6. And then t, and then the c value is 16. So I made a mistake on purpose because a lot of students make this mistake. Never assume a is positive, because if you're starting at a minimum point, a is negative. So that's the equation that models the depth of the tide as a function of time t hours after low tide. Okay. So for example 2 here, the function h equals this represents the depth of water h in meters in a river seaport where t is the number of hours after midnight. If the ship requires a minimum depth of 5 meters to clear the harbor and is ready to go by midnight, what is the earliest time the ship can set sail? Express your answer to the nearest minute. Okay. So what I'm going to do is first I'm going to factor out pi over 6 because I want to know what the horizontal shift is. Why do I want to know the horizontal shift? Because I am going to give myself a graph. So I'll just factor it out over here. So if you divide by pi over 6, that means you're multiplying this by 6 over pi, which is ending up being 6. So the max value is 4 plus 3, the middle plus 3. And the minimum is 1 because it's 4 minus 3. So 4 is the middle, 7 is the max, and 1 is the minimum. Okay, so we realize that k is pi over 6. So we can solve for the period if you want. So it's 2 pi over 6, which is 12. All right, everything so far so good. So we said 6 over here. So since you shifted 6 units to the right, that means, and it's sine, right? Sine starts at the equation axis, the middle of the wave. And since it's 12, can we not say that a quarter period is 3? So the question is, should I go down to minimum or up to maximum when you go backwards 3 hours? And the answer is you should go down to minimum, because what you can do from here, you graph the regular sine function because it's positive 3 here. There's no reflection on the x-axis, which means this point here must be a minimum if you go back 3 hours. If you go back another 3 hours, you're back at the equation of the axis. So that's our graph. And that's a really nice graph because you want to set sail. Your ship wants to set sail, but you need a depth of 5 meters in order to go safely. So let's say 5 is about here. Okay, and you are ready to go by midnight, but unfortunately, the depth at midnight is 4 meters, so it's not safe to go. So you have to wait, and then you can go. I am very interested in what that value of t is. Okay, not very, pretty picture, but the point is there. I need to solve for this moment right here. What value of t is it when the depth is 5 meters? Because there are infinite moments where the depth will be 5 meters, but I want the first moment because it's the earliest time the ship can set sail. So basically, this is a this is a trig equation now. Let h equal 5, and then we're going to solve this. And it's really important to draw this graph because this graph shows that you can't set sail right away. Because if I actually started higher, like if I started here and drew the rest of the wave, I can set sail right off the bat. So this graph shows that I have to wait. It's never a bad idea to give yourself a visual. So anyways, okay, let's solve this. Now, it doesn't matter which version, I'll use the unfactored. Okay, so remember I want the earliest time. So 5 minus 4 is 1, so I get 1/3. Not very pretty. Let me clean that up a little. Okay, so 1/3, unfortunately that ratio is not a friend of mine, so I'm gonna need my calculator here. Make sure it's in radian mode, of course. By now you should really have that. So this angle here is approximately 0.3, let's say 34. It's 340. And I'm going to do this 2k pi thing, because I actually want the infinite moments to show you some really cool relationship here. So that was quadrant 1. So I'm going to show you quadrant 2. So I'll do pi minus, because that's how I'm going to get the quadrant 2 angle. Okay, any angle coterminal to the first quadrant or the second quadrant angle. So I'm going to solve it. This one here. So add by pi and divide it by pi over 6. And if you take 2k pi divided by pi over 6, you get something really nice. You get 12k. And that's really good. I really want to see this 12k. Why? Because it shows my math is correct. It shows that my period is indeed 12. Everything checks out. So I just like to show this, just to see this beautiful relationship I should get. It's basically reinforcing I'm doing it correctly. So this one is approximately 6.65 plus 12k. So they want the earliest time. Okay, so do I want 6.6? Do I want to wait 6.65 hours or 11.35 hours? And the answer is, of course, I'm going to wait 6.65 hours. And I would definitely not wait till wait 11.35 hours, because if that's the case, I will be right about at this point, and it's very dangerous. I set sail, and then I'm going to crash because the depth drops below 5 meters. So setting sail right at this moment is actually a really good idea because it gives me a lot of time where the depth is above 5 meters. Anyways, therefore, the earliest time the ship can set sail is, okay, let's see. So 6.65, we want to take this 0.65 and change it to minutes times 60. So we're looking at 38.9. So I'm going to be safe. I'm going to round it to 39 minutes. So it's 6:39 a.m. That's the earliest time I can set sail. All right, so over here, ooh, our classic Ferris wheel question. Radius of 14, remember the radius is the amplitude because it shows you how far up and down you can go from the center of the wheel. I'm going to draw the graph, not that I need it, but I'll draw it anyways. So it makes 14, the bottom was 2.5 meters above the ground. So the min is 2.5. The middle will be 16.5 because you add by 14. Add by 14 again, it's 30.5. When is the rider 7 meters off the ground? If he gets on at the lowest point, okay, so he starts at the bottom of the Ferris wheel. And 1 revolution is 30 seconds. Okay, so if that's the case, the value of k is 2 pi over 30, which is pi over 15. We know the amplitude is 14. The c value is max plus min divided by 2. So it's 30.5 plus, 30.5 plus 2.5. That's 33 divided by 2, which is 16.5. For the d, the parameter d, that depends on what you, how you want to visualize this graph. Obviously, I'm going to start to choose this point. I'm choosing this point as my starting point for my graph. Because if I choose this to be my starting point or this point or any other point, I'm going to have to introduce a horizontal shift, and I don't want that. So I'm going to choose this point, so that means my equation, so h is equal to negative 14, negative because you start at a minimum, cosine pi over 15t, so no horizontal shift, 16.5. All right, so there's my model. This is really critical because if this is wrong, then really there's no point in progressing. When is the rider 7 meters off the ground? So there's a big problem with this question. Not a problem, but you should really look at it and say, it doesn't tell me when he's getting off the ride. He's on this ride forever. For all I know, he lives on this Ferris wheel. Okay, so if the question is asking when is the rider 7 meters off the ground, all I have to say is there are infinite answers. If I make the assumption, I don't know when he's getting off the ride, so I'm going to give you all the moments he is 7 meters above the ground, because I'm going to make the assumption he's living on this wheel, because I don't know when he gets off. So my expectation is I'm getting an infinite number of solutions. There is no restricted domain for this model. Okay, so I know it seems weird, but there are going to be infinite moments where he is 7 meters off the ground. So usually we will word the question something like, when is he 7 meters off the ground on the 3rd revolution? Or if he's on the ride for 7 minutes, when is he 7 meters off the ground? Okay, but doing what I'm doing is the hardest, I would say. You get all the answers and then you reject the ones based on the restricted domain. Okay, so 7 minus 16.5 divided by 14. So we're looking at 19 over 28 equals cos of pi over 15t. So how do I get my infinite answers? I have to study the coterminal angles. So pi over 15t is equal to, unfortunately, it's not one of my friendly ratios here. So we're looking at 0.825 plus 2k pi, fourth quadrant, so 2 pi minus 5.458 plus 2k pi. K is an integer. So now you'll see something really nice. Times 15 divided by pi. So it's about 26.1, let's say. And this becomes your 30k, which makes sense because after every 30 seconds, I'm back at where I started. If it takes 30 seconds, to complete one full revolution, this makes perfect sense. It takes me 30 seconds to be back at one point on the Ferris wheel. And here, let's see, 15, so inverse cos 19 divided by 28, and then times 15 divided by pi. So this is 3.9, let's just say 3.9 because I rounded one decimal place over there. So it's 3.9 plus 30k. So therefore, the rider is 7 meters off the ground after approximately 3.9 seconds, and every subsequent 30 seconds, and approximately 26.1 seconds, and every subsequent 30 seconds from that point. I'm sure there's a more fancy or elegant way to write it, but I really want you to see that if I didn't tell you when he's getting off the Ferris wheel, we can't really say how, we don't really know how many solutions there are. So we'll go with the infinite solutions. We assume that this Ferris wheel will never ever break and he's never getting off. So 3.9 seconds and every subsequent 30 seconds after 3.9 seconds. And 26.1 seconds and every subsequent 30 seconds from that, from 26.1 seconds. There is actually a restriction on domain. It's t is greater than or equal to 0. So that's why I can't accept the negative solutions from this and from this. So technically I shouldn't let k equal integers. I should let k equal whole numbers. But you know what? That's fine. You've by writing this statement, you've rejected negative solutions. Okay, so last one to go. A weight hanging from a spring is set into motion, moving up and down. Its distance d in centimeters above or below its rest position is described by the given equation here. So at what times during the first 2 seconds is the weight at rest position? So what I'm going to do is I'm going to find the infinite solutions, the infinite number of solutions that satisfies the equation, and then I'll reject it because I'm working with, I only want the solutions that fall within the first 2 seconds. So d equals 0. Oops. And then the 5 is, you can divide both sides by 5. Okay. There are a few strategies here. You can square both sides, but we're going to introduce a lot of extraneous roots. So what I'm going to do is set it equal to sine 6t equal 4 cos 6t, and then I'm going to divide both sides by cos 6t. Now when you divide by cos 6t, be very careful because you don't want to lose solutions. Now you're going to say, so what you're on the side, right? Cos 6t cannot be 0, right? You're dividing both sides not by 2, not by 3, by cos 6t. And we cannot divide by 0 to both sides, so we can't let cos 6t equal 0. So the question is, when is cos 6t equal 0? So cos t is equal to 0. So remember the cosine function is at an odd multiple of pi over 2. So cos t is equal to 0, an odd multiple of pi over 2. But this is cos 6t. Okay, so if you think about it, it's still an odd multiple, but not of pi over 2, but of pi over 12. Because if you think of the graph of y equals cos 6t, you're basically taking cos t and applying a horizontal compression by a factor of 6. You're taking a horizontal compression by a factor of 6. The period is no longer 2 pi. It's now going to be pi over 3, right? Because it's 2 pi divided by 6. Anyways, these are values that t cannot be. Luckily, if you take these values and sub it into the original equation, they don't solve the equation. So we have nothing to worry. But we should still write the restriction. I don't want you always just dividing both sides by cos 6t or some trig function and just be nilly-willy about it. You should really think. Okay, so this is going to be tan 6t equals 4. Tan. Tan is a friend, but 4 is not. 4, I have to use my calculator. So 6t is approximately 1.326 plus k pi. It's k pi because it's tan, and tan solutions are very nicely structured. It's either 1,3 or 2,4. So divide by 6. Let's look at 0.22, let's say, and pi over 6. K. It should be k pi over 6. Yeah, doesn't matter. Just we want the pi to be at the right side, preferably. Okay, I forgot to tell you, k is an integer. Okay, so I have all the infinite moments in time where this spring is going to be at the rest position. Now, since t is restricted, so first 2 seconds, 0 to 2, therefore, we have to reject quite a few solutions. Therefore, the weight is at rest position after, okay, so 0.22 we're going to take, of course, 0.22 seconds. And what you're going to do, you can add pi over 6. So can we take 0.74? Yep. Can we take 1.27? Yep. 1.79? Yep. No. So we gotta stop at 2.31 because that's beyond 2. So there's 4 moments. So the weight is at rest position after, let's say approximately during the first 2 seconds. When in doubt, take these 4 solutions and sub it back into the original equation. And they should make left side equals right side. Well, approximately, because these are all approximate solutions. Okay, so that's solving the trig word problems. But I would first recommend you to really master your ability to solve trig equations and then try these word problems. Because if you can't solve the regular trig equations, then these ones will be rather difficult. And I also want to mention that some of the questions you don't have a model, like we don't give you the equation, and some of them we do give you the equation. So you have to be comfortable. If I don't give you the equation, you have to be very comfortable to create the equation, whether you give yourself a diagram, give yourself a graph. Yeah, you have to be able to make the equation, because without the equation, there's nothing to solve. Anyways, we'll do the review sheet and the homework sheet, and that would be the unit.